Hello, dear students. Today we are going to see chapter 11, Modern Atomic Theory. Let's begin by the nuclear model of an atom. The atom has a small and dense nucleus, this one, and the nucleus is positive charged, contains the protons, and also contains the neutrons. But the neutrons are neutral, so the charge is positive according with the number of protons. And most of the atom is empty space, and it contains the electrons that are moving around the nucleus in orbit. And the charge of the electrons is -1. Remember that the nuclear charge and positive is balanced by the n electrons moving around the nucleus. What are the electrons doing? How the electrons are arranged and how do they move? That's what we are going to study today. Let's see. Different wavelengths of electromagnetic radiation. One of the ways in which energy travels through the space is in form of waves. Remember that light has a dual behavior as wave or as a particle. And remember that the visible part of the spectrum is the one that we can see and goes from 4 to 10 to the minus 7 to 7 to the times 10 to the minus 7 meters. The distance between these two parts of the wave or between these two parts of the wave is what we call wavelength. And we use this Greek letter to, uh, to speak about the wavelength. Then is the distance between two peaks or throats in a wave. Frequency is the number of waves or cycles per given time period that pass a given point in the space. The speed of the light, c, is a constant, and it is 2.9979 times 10 to the 8th meter per second. We can work with 3.0. We can approximate this constant in our exercises. The constant of light is the wave of length times the frequency. Don't forget about this formula. We are going to use this formula in the problems during this chapter. So the wave of length is equal to the constant of the light divided by the frequency of the wave. Well, we can picture an electromagnetic radiation, as I told you before, as a wave or as a stream of individual packets of energy that are called photons. Then you have a dual behavior of light as a wave or as particles. Here you can observe that the energy of, um, of the wave of length is different according with the wave of length and the frequency. We can find out the energy of a wave of a wave. For example, here uh, the atoms receive an energy and become excited. Then they jump from one level in a base state to a higher level when they receive energy. Then when the electron is excited, the electron can return to the original or lower energy state, but will emit certain kind of energy. The difference of energy in this case will give me the amount of energy that is absorbed or emitted by the atom when it goes to an excited state. For example, here we have hydrogen. Um, when hydrogen is excited in the excited state, can an atom of lowest possible energy state is said to be in the ground state. Then the excited state will absorb energy, and this energy can be released when the electron return to the ground state. Remember that the energy can be released in form of a photon. Here you can see the ground state and the excited state, and here you can see when the atom returns to the ground state energy, a, a photon is emitted, and the energy of this photon is equal to k, that is a constant, times the frequency. The levels in an atom of the electrons in an atom are quantized. It means that the electrons cannot go wherever they want. They can go from the ground state to an exacted energy level. For example, here we have the electron can jump from this state to this state, or to this state, or to this state. If we go to the spectrum, the emission spectrum of hydrogen, we can observe these lines that are here. If we know the, the wave of length of these lines, we can calculate the energy of the different um, jumps of the electron in the hydrogen atom to excited levels. Since only certain energy changes occur, the hydrogen atom must contain discrete energy level. Is what I wanted to tell you, that the electrons can jump only to certain levels, and this level of energy are quantized. The energy levels of all atoms are quantized. You can imagine it or make a representation like the, the different steps in a stair. Every stair will represent a level of energy in the atom. Why is it significant that the color emitted from hydrogen emission spectrum is not white? How does the emission spectrum support the idea of quantized levels? Well, this is an important question. Now, you can tell me you have seen the colors of the lines in the hydrogen spectrum here. What does it mean? Why they have a specific color? Because they have a specific wave of length, and the meaning of that is that the levels of energy are quantized. So they jump into levels that are already quantized, as you can see here in this stair. The same happens in the atom. That's why the light is not white. It has different colors because every color represents or a line represents a wave of length, and according with this wave of length, you can calculate the energy of the that the electron use in order to go to an excited state. So here you have a concept check question. You can stop the video at any time and you can study this question. We studied the Bohr model of hydrogen. He quantified three levels of energy, and that's why we can observe three lines of different color in the hydrogen spectrum, because this line represents the jump between levels by absorbing or emitting photons of particular wave of length. The Bohr's model of the atom was incorrect because the electrons do not move in circular orbits as we have seen before. According with the mechanical quantum, the orbitals are the region of the space where you can find with a higher probability the electron. They do not have sharp boundaries. Chemists arbitrarily define an orbital's size as the spheres that contain 90% of the total electron probability. Hydrogen has discrete energy levels. The energy levels are called principal energy levels, and they are indicated by whole numbers. For example, level 1, level 2, level 3, and level 4. Each principal energy level is divided into sublevels. For example, in level 1, you have one sublevel, but in level 2, you have two sublevels. In level 3, you have three sublevels, and so on. And these sublevels are represented by letters. and the letters indicate the shape of the orbital. So we can see, for example, orbital S, but look at this. The orbital P can be Py, Px, or Pz, and they are helicoidal in the directions of the axis in the space. The number tells the principal energy level. The letter tells the shape. For example, S means spherical orbital. P means two lobed orbital. The X, Y, or Z subscripts of the p orbital label tells along which of the coordinate axes the two lobes lie. Why does hydrogen atom have so many orbitals and only one electron? An orbital is a potential space for an electron. Atoms can have many potential orbitals. That's why you can see many different um, orbitals, possible orbitals for only one electron. Atoms beyond hydrogen. Let's see what happened. The Bohr model was discarded because it did not apply to all atoms. Only can be applied to hydrogen that has only one electron. But what happened? The spin of an electron is one property that helps to determine how the electrons is arranged in an atom's orbital. Look at this. Suppose that you have in one orbital, I'm going to represent using this square. Well, if you have two electrons in every orbital, one is going this direction, and this is going to go in the other direction. This is what we call the spin um, uh, the spin number. What does it mean? That in the same orbital you can have as much as two electrons, but in order to lower the repulsion between two negative charges in the same place or in the same region, what they do in real life. One is orbiting or spinning, for example, in the same way as the clock, and the other one goes opposite to in the opposite direction of the hands of the clock. The Pauli exclusion principle says that an atomic orbital can hold a maximum of two electrons, and these two electrons must have opposite spins. This is the spin. One goes like the clock, and the other goes opposite to the clock. The principal components of the wave mechanical model of the atom are: atoms have a series of energy levels called principal energy levels, N and D, and they can take whole numbers, for example, 1, 2, 3, etc. The energy of the level increases as the value of N increases. Then level 1 has less energy than level 2, and level 2 has lower energy than 3, and so on. Each principal energy level contains one or more types of orbital that are called sublevels. The sublevels are represented by letters. So the n value is always used to label the orbitals of a given principal level and is followed by a letter that indicates the type of shape of the orbital. For example, 1s, 3p, and so on. An orbital can be empty, or it can contain one or two electrons, but never more than two. If two electrons occupy the same orbital, they must have opposite spins. One this way, the other this way. The shape of the orbital does not indicate the details of the electron movement. It indicates the probability distribution of an electron residing in that orbital. So for an s orbital is a sphere, then you have a high probability to find the electron in this region. But if you, let's take for example the px, this is a type of orbital that have this form. And this is the region of the space where the electron have a high probability to be found. Here you have a concept check. Stop the video and you have already the answer. Let's go to the following information. Electron configuration is 1s1. The orbital diagram use a notation where 1 is the level of energy, S is the form of the orbital, and this exponent represents the electrons in this orbital. You can also represent, if for example, helium has 2 electrons in 1s. You can also represent using this representation, or this way, or this way. For example, lithium has the atomic number of lithium is 3. You can find this in the periodic table. Well, what does it mean? That you have 2 electrons in the level 1 orbital s, and you have 1 electron in second level orbital s. You can also represent by this way. Here you have oxygen. Well, now I'm going to speak about the electron configuration and the sublevel last occupied by the first 18 elements. Here you can see in this table how hydrogen, lithium, and sodium has only 1 electron in the outermost shell, and in the case of hydrogen that is in period 1 is in 1s1. In the case of lithium is in period 2, sodium in period 3, and so on. Beryllium and magnesium that are in group 2, they have 2 valence electrons. And what does it mean? That they have 2 electrons in the outermost shell, and they are, look at the periods where they are, and so on. For example, boron and aluminum have 3 valence electrons. Carbon and silicon that are in group 4, 4 valence electrons, and so on, until as you can see here, the noble gases. The inner electrons are the core electrons, and the valence electrons are the ones that are in the outermost, highest principal energy level of an atom. For example, how many ampere electrons does the element cobalt have in its lowest energy state? Well, first of all, you have to go to the periodic table. If you go to the periodic table, you can find out that cobalt has the atomic number of cobalt is 27. 27 electrons. That's the atomic number of cobalt. Well, according to this diagram, you begin here by 1s, 2s, 2p. The orbital s only can have as much as 2 electrons. The p can have 6, the d can have 10, and the F can have 14 electrons. So we are going to do this diagram, and I will show you how to do the representation. Okay, here we go. Look, when we arrive to the level 4, we go in until the orbital F. And same thing for level 5, sorry. Well, this now will go lowering 6, for example, goes until D, and the 7 goes until P. But you must follow the arrow in order to feel the electrons. So you follow these lines, and you can feel the electrons and represent the electrons according with the levels and electrons in every orbital. For example, let's begin by 1s, and you know that 1s can contain only 2 electrons. After this, we go to 2s. 2s can have 2 electrons. Then 2p, it can have 6 electrons. Until here, we have 10 electrons. We have to arrive until 27. That is the number of electrons in cobalt. Then we continue to 3s2, then 3p6, and then 4s2. Then until here we have 10 and 10, 20 electrons. We have 7 more electrons. Let's continue. After that, we go to level 3. Level 3 can have 10 electrons, but we need only, or we have only left 7 electrons. Then this is the electronic distribution for cobalt. Then we go to this level. We go to this level and we observe level D or orbital D has 10 electrons in 5 orbitals. 1, 2, 3, 4, 5. And we begin distributing the 7 electrons. We begin 1, 1, 1, 1, and 1. Until here we have 5, but we have 2 more. Then we begin pairing. 1 and 2. Now we have 7 electrons. How many of these electrons are non-pair or unpaired? Look, here you have 1 ampere, 2 ampere, 3 ampere, and that's the answer. Then, using this exercise, I show you how to use this picture or this diagram to fill the electrons of an atom and represents the distribution, the electron distribution according with this kind of notation. And then using the last level, I apply this notation to see how many electrons are unpaired. Look at this. You have here another question. Can an electron in phosphorus atom ever be in 3D orbital? Well, the answer is this, but you have to begin doing the distribution as I showed you before, and then you will give me the answer. Look at this. You can represent the distribution of an atom. For example, argon is supposed to be here. Then I can represent the distribution of potassium, saying that potassium is like argon. What does it mean? It's the atomic distribution of argon, in order not to write everything from the beginning. And then I know that the valence electron or the outermost shell electron are is only one, that is in level 4 orbital s. This is an abbreviated form of doing the representation of an atom, the electronic representation of an atom. Here you have another question that you can stop the video and you can see this is the answer. So we have to take into account that all the atoms in the period 1 will have the electrons in this orbital. For this one, in group 1 and group 2, the valence electrons will be in orbital s, while this one here will have always the valence electron in orbital p. And this block in between, that is also known as d block, because the valence electron will be in orbital d, and the lanthanides and actinides will have the valence electron in orbital in f orbitals. Remember that in a principal energy level that has d orbital, the s orbital from the next level fills before the d orbitals in the current levels. That's why I show you here in this representation that I fill first the s electrons in level 4 before the 3d electrons. Well, here you have the another exercise. Here you have the electron configuration for sulfur. You can use the developed representation or the short representation. And here you have for barium, and here you have for europium. You can stop the video and do this using the diagram that I showed you before. Remember that we divide the periodic table into metals, non-metal, and the metalloids. And also we studied that the energy that is necessary to take the outermost electron in the gaseous state of an atom, this energy is known as ionization energy. The ionization energy, when you go to the left of the periodic table, decreases. But if you go to the right, opposite, increases because it's more difficult to take an electron from one of the atom that is to the right than one that is in the left. That's why this property, the ionization energy, increases to the right and decreases to the left. And also decreases when you are going down in a group, decreases, and increases when you are going up in a group. This is in the period, and this is in the group. Look, this is the behavior of the ionization energy in a period. Now, in general, as we go down in a group, the first ionization energy decreases. Why? Because electrons being removed are an average, farther from the nucleus, and it's easier to take them away. So this is the behavior of the ionization energy in the group. And here you have which atom would require more energy to remove an electron and why? Of course, chlorine, because it's to the right in the periodic table. From lithium and cesium, oh, they are in the same group. Then, as lithium is up and cesium is down, of course, lithium will require more energy to remove the outermost electron from the gaseous atom. In general, the atomic size, as we go across the period from the left to the right, the atomic radius decreases. And in the group, when you're going down, increases. Look at this. In the period, decreases to the right, the atomic radius, and in the group, when you're going down, increases. This is the atomic radius, or also known as size of the atom. Here you have a question. You can stop the video. Here another one. Here another one. You have some questions that you can stop the video and you have already the answer. All what you have to do is to try to understand using. This is another type of exercise where you have to rearrange the atoms that are given according with the increasing ionization energy and according with the atomic size. As fluorine is to the left, to the right, and oxygen is to the right of sulfur, this is the order. This has lower ionization energy than fluorine. And atomic size is the opposite. Fluorine has the lowest atomic size, like sulfur has the biggest or largest atomic size. Well, that's all for this lecture. I hope to see you